So now we know what we're looking for. We're looking for a basis that has eigenvectors in it. So let's see if we can work it out for this example. Let's do it to make everything very precise. So want eigenvectors of -5 to 2, -2 to get v. So how can we find these eigenvectors? So we have to remember what are eigenvectors. So recall AV equals lambda v, and so A minus lambda times the identity v equals 0, which means this has a null space. Because it has a null space, we know what it does is it takes the space that it has as its input and it maps it to something which has been squashed, has been flattened. Because some particular direction in its input, it maps to 0. So it flattens the space. Because it flattens the space, we know that what it does is it has volume. It takes the unit cube, and its volume of the unit cube is 0. So in particular, we know that the determinant of A minus lambda I equals 0 if lambda is an eigenvalue. This particular characterization helps us find eigenvalues. Now, in reality, when you're using the computer, this is not the characterization that's used. The computer has other better ways of finding eigenvalues and eigenvectors. However, by hand, this is pretty useful. So we're going to try to do this. So let's look at this, and turns out to be useful. A minus lambda I. You can also use determinant lambda I minus A equals 0. Any of these work. So let's do one of these for this. So let's try to find the eigenvalues. So let's see determinant. Let's do lambda I minus A just to be different. Let's look at lambda plus 5, negative 2. So I'm subtracting this, remember. Negative 2, lambda plus 2. Let's look at the determinant of this. Well, for the 2 by 2 case in 16a, you worked out what the formula is. In general, we'll talk about it in another lecture of how you can compute it in general. So in this case, we multiply the entries on the diagonal and subtract the product of the off-diagonal entries. So this is lambda squared plus 7 lambda. And here we have 10. 10 minus 4 is 6 plus 6. So this factors immediately into lambda plus 6 and lambda plus 1. So eigenvalues lambda 1 equals, let's pick one of them to be the first one, let's say -1, and lambda 2 equals -6. So let's find, so far we've got the eigenvalues. What we need is the eigenvectors, right? This, remember, we want eigenvectors in here. So let's find the eigenvectors. How do we find the eigenvectors? Well, we can look at this matrix. So let's use the other one now, A minus lambda I. A minus lambda I. What do these equal? So for lambda equals -1, we have this matrix minus -1 times the identity. So what is this? -5 minus -1 is +1. 2, 2, -2, minus -1 is +1. This is just -4, 2, 2, -1. And we want to find its null space. So the null space of this, that will give us an eigenvector. Well, for this, it's pretty easy, right? We can just instantly see that if we take the first row and add to it 2 times the second, we're pretty good. That's going to give us 0. So we just have 1, 2. This is v1. Okay, so that gives us v1. Let's go for the other one. Lambda equals minus 6. What's the matrix? Minus 5 plus 6, 2, 2, minus 2, plus 6. What does that equal? Minus 5 plus 6 is 1, 2, 2, 4. What's the null space of this? Well, again, it's pretty clear that if I take the first row, multiply it by minus 2, and add it to the second, I'm going to get 0. So I have a second eigenvector. So now I have 2 eigenvectors. So this says, let's use v equals, let's put the 2 eigenvectors together. 1, 2, first one, and the second one, minus 2, 1. So for this, we can also compute the inverse. Remember, we need both of these. V inverse is just going to be, oops. So it's pretty easy to see. In this case, one can use an exact formula. So you get 1/5, 2/5, minus 2/5, and 1/5. It's always good to check. 1/5 times 1 minus 2/5 times minus 2, that's 1/5 plus 4/5 equals 1. 2/5 times 2 is 4/5. 1/5 times 1 is 1/5. Again is 1. Again, let's check. 1 minus 2 on this is going to clearly be 0. So this is working out. Let's make that pretty neatly. So we have these. So if we do this, what's happening? Right? Let's take a look. So our x tilde differential equation, d by dt, x tilde, is just going to be the diagonal matrix of eigenvalues, minus 1, 0, 0, minus 6, times x tilde. So from this, we can easily solve. So x tilde of 1 as a function of time is x tilde, the first component, evaluated at time 0, times e to the minus t. And the time function for the second component of x tilde is going to be its initial condition times e to the minus 6t. So what is the initial condition? Well, let's look at the picture again. To go from these coordinates, the original coordinates, to the tilde coordinates, we have to multiply by v inverse. So this is just v inverse times the initial condition for x. Now, in this example, remember, the initial condition for x was 1, 1. So this is going to be 1/5, 2/5, minus 2/5, 1/5, times 1, 1, which is equal to what? 3/5 and minus 1/5. So now we know exactly what x tilde of t is. X tilde of t is just 3/5 e to the minus t minus 1/5 e to the minus 6t. Now, how do we go from x tilde, the solution to the in the new coordinates, the nice coordinates, back to the original? We multiply by v. So that means that Let me write this more cleanly. X of t is just v times x, oops, v times x tilde of t, which in this case, hold on, let me zoom in here. So recall, what's the V matrix? 1 minus 2, 2, 1 times this, 3/5 e to the minus t minus 1/5 e to the minus 60. What does this equal? Well, this equals 3/5 e to the minus t plus what? Minus 2 times this, 2/5 e to the minus 60. And then what do we get here? We get 6/5 e to the minus t minus 1/5 e to the minus t. So we've managed to solve it, this time without getting any magical hints. Notice this agrees with what we got using the magical hint. So the two give us the same answer, which is the right answer. So for these problems now, we have an approach. Given any system of differential equations, whatever that system of differential equations is, if it can be expressed in vector matrix forms using a constant matrix A, we look for a basis that's an eigenbasis for the matrix A. Namely, we find all of the eigenvalues and eigenvectors of that matrix. We find the basis of all the eigenvectors, if such a basis exists. We change coordinates to this. Having changed coordinates to this, we then solve the system of scalar equations, which in this case are completely decoupled from each other. They're diagonal, after all. And given this, so this is this example of a diagonal thing. They're diagonal, just solve them in a decoupled way. We apply the initial condition. Having got the initial conditions and having the solution in the nice coordinates, we simply use the same basis of eigenvectors to change back to the original coordinate system, where we have now a solution to the original system of differential equations. This is how we can get the computer, which can easily compute eigenvalues and eigenvectors, to solve systems of differential equations for us. Now, next time, we will go beyond this to see if we can do even better from the perspective of understanding. But that's next lecture.